This video is going to run through graphing rational functions by hand. We're just going to start by doing an example. For the rational function f of x equals 2x plus 1 divided by x, we're going to find the domain, find the asymptotes, find the intercepts, and then use all of that information to create a graph. So to find the domain of a rational function, we look at the denominator, and the denominator can't equal 0. That's because division by 0 is undefined. So in this case, x cannot equal 0. In interval notation, our domain is -infinity to 0 and 0 to infinity. Find all asymptotes. To find our vertical asymptotes, we look at zeros of the denominator, as long as there isn't a common factor. And this particular rational function, there's no factoring I can do, there's no common factors. So I'm going to take my denominator, which is x, set it equal to 0, and that's my vertical asymptote. To find horizontal asymptotes, we learned that there are 3 different cases. If you want to see how to find horizontal asymptotes in more detail, please look at the previous video. But this is the situation where the degree of the numerator is equal to the degree of the denominator. I have a 2x in the numerator and a 1x in the denominator. When you have the same degree in the numerator and the denominator, your horizontal asymptote is the ratio of those leading coefficients. So we have a 2x over 1x, so my horizontal asymptote is y equal 2 over 1, or y equal 2. All right, so vertical asymptote, x equals 0, horizontal asymptote, y equal 2. Find all intercepts. To find the x-intercept, we have to plug in 0 for y, or plug in 0 for f of x. So I have 0 equals 2x plus 1 divided by x. The only way a fraction can equal 0 is if the numerator equals 0. So I'm going to set 2x plus 1 equal to 0. I can solve for x by minusing the 1 and dividing by 2. So I have an x-intercept at x equal -1/2. To find my y-intercept, I plug in 0 for x. So 2 times 0 plus 1 divided by 0. Well, division by 0 is undefined. And in fact, 0 is not in our domain. So that means there is no y-intercept. So the only intercept we have is at the point x equal -1/2, y equals 0. So finally, we're going to put all this information together and create a graph of this function. I'm going to start by plotting any of the intercepts that I found. I have only one intercept here. I have the point -1/2, 0. So I'm going to start by putting that into my graph. Then I'm going to really lightly sketch maybe dotted lines to represent my asymptotes, just so I can keep track of where those asymptotes are. I have an asymptote of x equals 0, and another one of y equal 2. So I lightly sketched in some dotted lines to guide me with those asymptotes. And then we can piece together most of this graph just using the information we already have. For example, when I look at the left side of this graph, so to the left of that x-intercept, I know that the graph has to approach my horizontal asymptote. The horizontal asymptote describes the end behavior, and because I have only one x-intercept, this graph can't go up and then down and up and down. I know that it has to just approach that horizontal asymptote. So on the left side, our graph is approaching our horizontal asymptote. And then on the right side of that x-intercept, we have to be approaching our vertical asymptote. So my graph should go down towards x equals 0. Then on the other side of the graph, or I should say the other side of my vertical asymptote, I don't have any points to guide me on where that graph is. So I'm going to pick an x value that's bigger than 0, just so I have at least one point to help me guide this graph. And I chose x equal 1. So I'm going to take x equal 1. I'm going to plug that into my function. So I got 2 times 1 plus 1 divided by 1. That's 3. So that tells me the point 1, 3 lies on this graph. So I went ahead and I plotted the point 1, 3. And then I can use the same reasoning to create my graph. As I go to the left from this point, I'm going towards that vertical asymptote, and I should be going up. I know that the graph is not going down towards that vertical asymptote because there are no x-intercepts. There's no other x-intercepts, so it has to be going up. And then on the right side of the point that I graphed, I know that we have to be approaching our horizontal asymptote. So I've drawn that graph approaching that line y equals 2. If you're having a hard time drawing these graphs, it's not wrong to plot a couple extra points just to make sure you have things in the right direction. But what we're trying to do is really create a rough sketch that shows our intercepts and our asymptotes. And so if you can do that without plotting extra points, that is totally fine as well. Let's do another example. I have the rational function f of x equals x minus 2 divided by x squared minus x minus 2. Before I do anything else, I want to get this in factored form. And I notice that we can factor the denominator. Negative 2, let's see, product of 2 has to be 2 and 1. And if I choose a negative 2 and a positive 1, that does add up to negative 1 for that negative 1x term. So this function in factored form is x minus 2 divided by x minus 2 times x plus 1. To find my domain, I know that the denominator can't equal 0. Division by 0 is undefined. So I'm going to take that denominator, set it not equal to 0. Since I've already factored the denominator, I can solve by setting each of those factors to 0, and I know then that x cannot equal 2 or negative 1. Those are the zeros of my denominator. In interval notation, that's going to be everything from negative infinity to negative 1, not including the negative 1, and then everything from negative 1 and 2, and then everything from 2 to infinity, again, not including that 2. So domain, denominator can't equal 0. To find my asymptotes, I want to look at zeros of the denominator as long as they are not part of a common factor. And in this particular problem, we actually have a common factor of x minus 2. That means there is a hole in the graph at x minus 2, or a removable discontinuity at x equal 2. So the only zero of the denominator that doesn't correspond to a common factor is the x equal negative 1. So I have a vertical asymptote at x equal negative 1, and I do have a hole at x equal 2. For my horizontal asymptote, the degree of my numerator is smaller than the degree of my denominator. Our leading term in the numerator is x. Our leading term in the denominator is x squared. Anytime this happens, we have a horizontal asymptote of y equals 0. So asymptotes at x equal negative 1 and y equals 0. All right, find all intercepts. To find my x-intercept, I plug in 0 for y. So I set my function equal to 0. Now, that x minus 2 corresponds to that removable discontinuity, or hole. That's a common factor. We could actually, at this stage, cancel out that common factor. And what that means is, I guess if we were to cancel it out, we would have a 1 left in the numerator. But basically, the only thing with an x in the numerator is part of this common factor, represents this hole. And so there is no x-intercept. Or another way of thinking about this, just like we saw in the last example, x-intercepts occur at zeros of the numerator. Zeros of the numerator. The only way a fraction can equal 0 is if the top is 0. The only 0 of the numerator here is x equal 2. But x equal 2 is not in the domain of this function. There's a hole at x equal 2. So therefore, this function does not have an x-intercept. What about a y-intercept? I'm going to plug in 0 for x. I got 0 minus 2 divided by 0 minus 2 times 0 plus 1. That simplified all the way down to 1. So I do have a y-intercept. My y-intercept occurs at y equal 1. All right, finally, let's put all this information together and create a graph. So once again, I'm going to start by graphing any of the intercepts that I found. I have only one intercept. It's at the point 0, 1. Then I'm going to very lightly sketch in my asymptotes just as guides. I have an asymptote at x equal negative 1. So I very lightly drew a dotted line of x equal negative 1. And then my horizontal asymptote is y equals 0. All right, so to create my graph, I'm going to start by looking at the one point I have graphed. And if I go to the right from this point, the graph has to be approaching that horizontal asymptote. So I'm going to draw something that is approaching that horizontal asymptote. However, if we look at our work, x equal 2 is not in the domain of this function. There is a hole at x equal 2. And so I'm going to just go ahead and right where x equal 2 is, I'm just going to erase a little bit and draw an open circle to indicate that there is a hole at x equal 2. Now, if I go from this intercept that I have and I go to the left, we have to be approaching our vertical asymptote. I know that the graph is not going to go down because there aren't any x-intercepts. So the graph has to go up towards that vertical asymptote. On the other side of that vertical asymptote, to the left of x equal negative 1, unfortunately, I don't have any information. So I'm going to plot another point by just picking an x value and plugging that into my function. So I chose x equal negative 2. That's smaller than negative 1. I plugged that into my function, and I got y equal negative 1. So I know that when x is negative 2, the y value is negative 1. Then to draw my graph, as I go to the left, this function has to be approaching my asymptote. So it has to be approaching y equals 0. And as I go to the right from this point, we have to be going towards that vertical asymptote. I know it has to be going down. Again, it's not going to go up because there are no x-intercepts. So it has to be going down towards that vertical asymptote. And there's my rough sketch of this function. All right, I want to do one more example. Let's see if we can sketch the graph of f of x equals x squared minus 4 divided by x plus 1. Once again, I'm going to start by finding the domain. To find the domain, the denominator can't equal 0. X plus 1 cannot equal 0, so x cannot equal negative 1. And my domain would be negative infinity to negative 1, negative 1 to infinity, not including that negative 1. So everything except negative 1. Find all asymptotes. To find the vertical asymptote, I'm going to set the denominator equal to 0. Now before I do that, I should really make sure that there aren't any common factors. And this numerator, x squared minus 4, can be factored as x plus 2, x minus 2. So I can see that there are no common factors. That means there's no removable discontinuities or holes. And so I'm just going to set the x plus 1 equal to 0. I got a vertical asymptote of x equal negative 1. Now for my horizontal asymptote, this is the situation where the degree of the numerator is bigger than the degree of the denominator. When the degree of the numerator is bigger than the denominator, there is no horizontal asymptote. However, this problem is going to have a slant asymptote because the numerator is only 1 degree bigger than the denominator. To find our slant asymptote, we're going to go ahead and use division. We're going to actually do the division that's described in that rational function. And we can use either long division or synthetic division. I'm going to use synthetic division. I'm dividing by an x plus 1, so I'm going to write down a negative 1. And then I write down the coefficients of the polynomial. We have 1x squared. There are no x terms, so 0x, and then the constant is minus 4. So I wrote down a 1, 0, minus 4. Using my synthetic division, I brought down the 1. 1 times negative 1 is negative 1. We add, I get negative 1. Negative 1 times negative 1 is positive 1. I add, I get negative 3. That negative 3 is going to be my remainder. And so technically this division means when we do this division, when we find this quotient, we are going to get 1x minus 1, x minus 1, plus the remainder, which is negative 3 over the divisor. So plus negative 3 over x plus 1. And the idea is this remainder term, when x gets really, really big, is going to go to 0. And so our slant asymptote is just the 1x minus 1. Y equals 1x minus 1. So we have a vertical asymptote at x equal negative 1 and a slant asymptote of y equal x minus 1. Find all intercepts. To find my x-intercepts, I set the function equal to 0. The only way a fraction can equal 0 is if the top equals 0. So the numerator is my x squared minus 4, which factored to x plus 2, x minus 2. So my numerator has zeros of negative 2 and 2. I have two x-intercepts, one at negative 2 and one at positive 2. Y-intercepts, I'm going to plug in 0 for x. When I plugged in 0 for x, I got negative 4 over 1, or negative 4. So I have a y-intercept at the point 0, negative 4. So there are my intercepts, 2, 0, negative 2, 0, 0, negative 4. Finally, let's put all this information together and create a graph. So first thing I'm going to do, just like in the other problems, is I'm going to plot all the points that I found. So I have an x-intercept at negative 2, another x-intercept at positive 2, and my y-intercept is negative 4. Then I'm going to sketch my asymptotes just very lightly as a guide. We have a vertical asymptote of x equal negative 1. So I just drew in that vertical line, x equal negative 1. I have a slanted asymptote, y equal x minus 1. That's a line that has a y-intercept of negative 1 and a slope of positive 1. So up 1 over 1, up 1 over 1. And I drew that line really lightly as a dotted line. Now I'm going to try to create my graph. So I'll just work my way from left to right. So starting at that leftmost intercept, as I go to the left, the graph has to approach that horizontal asymptote. That horizontal asymptote is describing my end behavior. So as we go to the left, our function has to approach that slanted asymptote. As I go to the right from that intercept, we're going to have to go up towards that vertical asymptote. On the other side of that vertical asymptote, I see my y-intercept. From that y-intercept, as we go to the left, we're going to have to drop down to that vertical asymptote. Again, we can't go up because there's no other x-intercepts, so it has to go down. And then I'm going to connect the graph from my y-intercept to my x-intercept. And then to the right of my x-intercept, as we go to the right side of the graph, we have to be approaching that slant asymptote. And there's a rough sketch of the graph of this function. That was my last example. As always, please let me know if anything in this video is unclear.